In this video, I'm going to go over the concept of centroids again. When we're dealing with problems in statics or strength of materials, we often need to find where the center of gravity or center of mass or center of an area of a shape or volume is. And we'll start with some really basic symmetric shapes. If we have a symmetric shape, it's always pretty easy to find the centroid. I guess before we even look at specific shapes, let's just remind ourselves what a centroid is. Basically, it's the location at which all of the areas that surround that point are balanced, or all of the masses, all of the forces. It's basically the point about which whatever quantity you're considering, whether that's area, mass, etc., those all balance or equally weighted about one point. So for example, if I take a look at this calculator, I look at it, we can see that it has one axis of symmetry, right? If you run a line right down the middle of the calculator, it's mirrored relatively left to right. It's not quite mirrored, I guess. There's a solar panel that's not quite symmetric. But in general, we would consider this a fairly symmetrical object about that axis. And if we're looking in 2D, if we look about another axis this way, there's no real spot about where there's an axis of symmetry. So if we were going to try to find the centroid for this object, ignoring again the eccentricity of that solar panel, we would be confident in saying that that centroid is going to lie somewhere along the axis that runs right through the middle of this shape. But as far as this direction, we can't intuitively guess where it is. We can estimate, looking at it, it's a little wider on the bottom, so the centroidal axis will be probably a little closer to this end than to this end. And if we wanted to find it experimentally, if we're trying to find the center of gravity or center area of a two-dimensional shape, we can always do that kind of experimentally by just seeing where's the balance around. So if I'm looking at in this direction, if I try to balance it there, I'm not there yet, still not there, getting closer, it's starting to... And so now I found a spot about which it balances roughly. So again, this is real rough, but that gives me the idea that basically I could find the centroid of this object by knowing I've got one axis of symmetry running down the middle, and then the intersection of that with this axis about which it balances, wherever that is, right about in there, is going to be the centroid of this shape. So that's kind of just thinking about it qualitatively, what a centroid is. If we want to look at it as far as quantitatively, how do we calculate it for a shape that's not as simple as that? Let's start with a really simple shape. If we just have a rectangle, any shape that has symmetry about it, it's really easy to find it, right? So if we look at this rectangle, it has two axes of symmetry. So one of them is right down the middle vertically, so something like that. And then the other one is right across horizontally. So that's right there. In simple shapes, you're just used to it from working with objects in your day-to-day life. You can kind of visualize where the centroid of a simple shape is, right? So there would be the centroid of this shape. When we start looking at more complicated shapes, here on this red kind of combination of shapes, it's not super easy to guess where the centroid is. There's no axis of symmetry. I don't see anywhere that I can mirror it. So if I wanted to truly find the centroid of this, I would have to look at it in both directions to find the centroid. If I pick this as my origin and say I'm moving in X in this direction and Y in this direction, I'd have to find where the centroid was. I'd have to find both Y bar or X bar. And just as a reminder, we say that X bar is the distance. I'm just going to guess somewhere, if this is our centroid, X bar is the distance to the centroid along the x-axis. So this would be X bar out to here, and Y bar would be up to here. But how do I find that? So the equation to find the centroid in its x and y coordinates is always going to be equal to either the integral, if it's a complicated shape like this, so we could say the integral of our individual x's times areas over the integral of just the areas. And so what that's saying is basically we're looking at individual pieces of this, how far that piece, that dA, let's sketch out some of these pieces roughly to make it more clear what we're talking about. So if I break this shape here, this irregular shape into slices, just like we do in calculus when we're integrating something. And I'm drawing these big, but anytime we're doing integrals, really we're looking at an infinitesimally small slice. But basically what we're doing is saying, in the middle, break it into these slices, and then roughly the middle of this slice is right here. So look at kind of that block is approximating that one. Okay, so now I've got these individual slices, and if I look at them, the area of one of these slices would be, this little individual, we call that a little dx, and then this distance here is our individual, that would be a kind of y for this particular one. And it's easy for us to find the centroid of one of these, right? One of these rectangles, it's going to be right here. So I can find that y tilde, or however you want to say the individual y. We can do that for rectangular shapes real easily. And then for this next one, it looks like it's a little taller. The centroid's going to be about there, so it will have its own y, and it will have its own area. That's going to be this dx times the overall y distance for that. So another centroid. This one's actually really close. These three in a row all are really close, and then another one up here a little bit, up a little bit, down a little bit. So if I take each of those, find the area for this rectangle, area of this rectangle, distance to the centroid of that rectangle, distance to centroid, this can basically, if we're looking at simpler shapes, if we're instead of integrating, we can look at it as another way of saying it's equal to the sum of the individual x bars times area over the sum of the areas. And that's only for in the x direction, right? In this particular shape, it doesn't have symmetry about x or y. So after I'd figured out what y bar, I set this one up here, right, to be finding y bar. I'm looking at the centroids along from distance from x-axis up, so that's for y. And then if I'm looking for opposite direction, I'm going to have to then make slices through here. And actually really on this shape, right, it's a composite shape, so I could look at all of this part down below as one. That's a really easy rectangle, but then I would be looking at individual slices vertically again. Okay. In these classes we relatively infrequently actually deal with irregular shapes that have curves like this, and if you do, you're probably going to be modeling that in a solid modeler like SolidWorks or AutoCAD or something anyways, where it can do all the calculations to find your centroids and whatnot. So that's more just kind of a conceptual talk about it. We may do a couple problems where you do it, find a centroid by calculus, but in general most engineering shapes that we're going to be considering are simpler than this. They might not be as simple as this though, right? This is super simple. You can see it just off the top of your head. Let's modify this rectangle here and look at, let's say we added a triangle onto the top of this rectangle now. So that triangle has a height of 4 units. Our previous rectangle had a width of 8, this one does 2, and a height of 10. So if we come back up and look at this original one, we didn't actually ever label it, but the centroid for this upper rectangle, the x coordinate, again if we're doing x and y, the x-coordinate for the centroid is half of 8, so it's at 4. And then the vertical component is half of 10, so it's at 4, 5 if we're looking at x and y coordinates. If we come down now and look at this triangle, this is not a simple shape, right? And I guess you could figure out the equation of this line and integrate. You could use the integral format of this, but we can find the centroid of a triangle relatively easily. If you don't remember it, in either of your books, whether you're in statics or strength of materials or dynamics, in our books they all have, either within the front cover or the back cover, they have a chart that shows the location of the centroid for common geometric shapes. So we're looking at a triangle, so it shows us that the centroid of a triangle is located 1/3 of the distance from the height. So from the base to the top, 1/3 of that is the centroid. So in this case, our centroid is going to be 1/3 of 4 units. So centroid, and I know where, for both these shapes, they're symmetric about this axis, right? So for this shape, I'm only going to have to do solve for y bar, basically. I need to find where the centroid is along this axis of symmetry, because I know by inspection that it's somewhere along here, right? And before we start actually calculating it, let's kind of just think through, where do we think it likely is? So if before, on the first rectangle, it was centered right at 4, 5, now we've added some area above that distance. Do we think the centroid is going to move towards that area, away from that area? Hopefully it makes sense to you that we would expect that the centroid is going to move up, move in the positive y direction, because if we think back to what the centroid is, it's the point that everything balances about. So if the shape was balanced about this axis right here, and then I added more area onto the top, now you can think about it as the whole thing is weighted more heavily to the top. So to balance it, we're going to have to move our axis closer to the positive y so that we get some more of this area down here to counterbalance the triangle we've added. So if we think back to, so now we're trying to find our distance to our unknown centroid, that we'll label this distance as y bar, and we said that the location of the centroid is equal to basically the weighted area, so sum of the composite y's, so each one, there's one y for each area over the sum of the areas. Okay, so let's start looking at that. We have two areas that are easy to find the centroids of. The first one is this lower rectangle. So if we're following this, so y bar is going to be equal to the distance from our y-axis to the centroid of the first shape. So that's the distance to this centroid here, which we said this centroid for, let's shade in these areas. Let's say we'll do this big green area is our first one, and then we'll call the triangle red. That'll be our second one. So y for the green area, distance to the centroid of it is half of the shape of it, so that's going to be 5. In this case we're working in centimeters, so 5 centimeters is the distance times the area of it is 10 times 8, so that's 80. So that's the top part. This is the weighted area of the green area, plus, now for the second one, distance we said to the centroid of this one, this distance is, we said 1/3 of the height of it, so that's 4/3. So the total distance there is 10, because anytime we're finding the centroid, we're finding it from some specific point. It doesn't actually matter what point I start out looking for. I could have found the centroid by looking about this axis or about an axis at the top. It doesn't matter which one I use to start with. I just need to be consistent when I find my distances from the individual centroids. So I did that first one from this centroid right here. This is the distance I used, right? I did 5. So if I use this location here as my origin for my distance for my first area, I have to use it for the second area as well. So that means my distance for the second area is going to be 10 plus 4/3, which that's 10, so 4/3 is 1 1/3, so that's plus 11.333. That's the distance from here, so we say 11.33 repeating. It's our distance to the centroid of the triangle. Okay, and then the area of the triangle is going to be 8 times 4 divided by 2, so 8 times 4 is 32, so it's going to be times 16. Okay, so that's the sum of each of the centroid distances times their area. And now I do the sum of the areas. So the sum of the areas is just 80 plus, second area was 16. So if I plug those into the calculator, 5 times 80 plus 11.3333 times 16, all of that divided by 96, I get it's equal to 6.055. So if we want to actually locate that, let's start by showing the original. Actually guessed pretty closely when I was just sketching on there. This right here at 5 centimeters is the centroid of the green shape. This up here at 11.33 is the centroid of the red shape. Now our composite centroid is at 6.055. So, wow, I guessed pretty close there on our original y-bar. So this right here, the centroid is located. So centroid at, along the x-axis, it's right on the axis of symmetry, so it's at 4, 6.055. So here I've cut out of cardboard a rectangle that matches that top one with a width of 8 and a base of 10, or height of 10. So I found axis of symmetry by just connecting the opposite corners, and where they intersect is the centroid. So that would be 4, 5 over. And so if we balance, that point on a pen, you can see that is roughly pretty close to where the centroid is, because it's balancing right on the tip of that pen there. So I also have cut out a scale shape of the rectangle with the triangle added to it. And we've got our axis of symmetry down the middle, and then we just figured out where our y-bar would be at 6.055. So if I measure up 6.055, that's going to be about right there. And just as a reminder, our previous centroid was at 5, which is about right there. So it shifted up just about 1 centimeter. And so let's mark that through to the other side. And let's see if it balances on that. And yeah, you can see it's balancing at that centroid. So it looks like we did a pretty good job finding our centroid for the rectangle, added a triangle. Let's say if instead of adding a triangle, we had removed some space from the original rectangle. Let's look at that mathematically. So we found the centroid when we added a triangle onto our base shape. Let's look at how we would find the centroid if we took away an area from our base part. Let's say we look at the same overall triangle again, 8 by 10 rectangle. But now let's remove this area in here. So again, we can look at it as composite areas. So let's start out by looking at the overall original triangle, that purple area. Our equation is still the same, and we still have an axis of symmetry, right? If we look at this shape, it's symmetric across its middle. So if we're looking at this is x and this is y, we know that we don't really need to do any work to find x bar because it's going to be located on the axis of symmetry of this part right down the middle. All we need to do is try to find out where our axis of symmetry, where our centroid or axis that would bounce across in this direction is. So that distance, right, is going to be y bar. So again, equation's same, y bar is equal to the sum of the individual areas, the distance to their centroid, so those y bars times the area of each part that contributes to the composite over the sum of the areas. So let's start writing those out. So let's do the big purple area first. So y bar is going to be equal to the distance. And we need to pick where we're measuring our centroids of each component piece from. Last time we did it from the bottom down here. Let's do it from the top this time. So this time we'll do all our measurements from up here, just to show, and maybe we'll repeat it when we're done, just to show that we come up with the same answer. Okay, so y bar, if we're measuring from the top, the center of this big shape, doesn't really matter, it's going to be the same, right? The distance is going to be 5 centimeters times the area of the big shape is 80. So again, let me do this in the color. So we're looking at the purple shaded area right now. So it's going to be 5 times its area, 80, and then plus the green area, in this case, is going to be, well, we can do this, we'll say plus to start with, because we're summing these. The distance of its centroid to the top is going to be 1, the distance to get to the edge of it, and then its side length is 1, so the distance to the centroid here is 1.5, so it's going to be plus 1.5 times, and now here it's going to be a negative number because this is an area we're saying we're cutting this out of our shape, so we're losing that weighted area. So its area is 1 times 6, so it's times -6. Okay, and then the bottom half of the fraction is just the sum of the areas, which is 80 plus an area of -6. So that comes out to equals 5 times 80 plus 1.5 times -6. So on top I get 391 divided by 80 plus -6, so that's 74. So we get 5.284 inches. Let's go back and look at that in our drawing. So we know that the original centroid of just the whole rectangle would have been at 5 centimeters, right? So that's right, roughly where I guessed. So now, in our distance, this time we measured from the top, right? So now rather than measuring up from the bottom, like I did when we were finding y bar here, right? Our distance came from the bottom up. Now we're looking from the top, so I measure from the top down, that 5.284. So the composite centroid is right about there. So there's the original, here's our composite centroid. So you can see that by subtracting this area, we had to move our balance point a little towards the bottom of the shape so that a little more of this area on the top can make up for that area we got rid of. Let's do the same thing, but just reference off of the bottom now. So we'll do it using, just do it y bar again. And it's still the same equation. It's the sum of the y's times the a's. We're just measuring the y from different location now. So for the first part, for the purple shape, it's actually going to be identical because the centroid of the overall parent shape is the same whether we're looking from top or bottom, right? It's 5 centimeters away. So it's 5 times 80, area hasn't changed, plus, now this one is going to change because now we're measuring from the bottom. So now our distance is going to be 10 up to the top. Minus 1 is 9. Minus a half is 8.5. So it's going to be the distance is 8.5 times, the area is still -6, right? We're getting rid of 6 square centimeters there. So minus times -6, and bottom is unchanged, right? It's going to be the 80 plus the -6, since we're removing it. That's why the 6. This is a whole of this shape. Okay, so that's equal to 5 times 80 plus 8.5 times -6. It's equal to 349 over the same 74. So we get 4.71. Oh, sorry. Put that down wrong. It's 4.716 inches. Okay, and so now we're measuring from the bottom instead of the top. And so if I measure up 4.7, there's 4.6, 4.7. You can see I'm landing at the same spot. So if I add these two together, I should come up with the overall distance that was between the 2 points I originally figured that out. So we can check ourselves there. 4.716 plus 5.284. 4.716 plus 5.284. Hopefully we get 10. Yeah, so equals 10. So we found the same location for the, it's this one here. This is original. This is the one once we cut out the shape. We found out that same distance from either the top or the bottom. It really doesn't matter where you pick. I could have picked some arbitrary axis here and used that to figure out the distance from that axis to the centroid of each of the composite shapes, and I would end up with finding that same location. Okay, last one here. Let's do one that is not symmetric about any axis. So we've got our same shape, right? A 10 by 8 rectangle, but now we're going to take out a rectangle that's 2 by 3 up in the corner. So we kind of have our original, really big (8 by 10), and then we're going to cut out that corner piece. So again, it's going to be just kind of same concept as up here when we're removing a part. The difference is now that we're going to have to find both X bar and Y bar, because if we look at it, it's no longer symmetric about this axis, right? Because this isn't centered right there. So now we're going to have to find both X bar and Y bar. So what we're going to look for is some composite centroid. And let's mark out where our original centroid before we remove a part would be. So that's going to be centered at 4. And then at 5. So we know that roughly right there is the centroid before we cut out the piece. So I just want to talk about, in your head, think about which way do you think the centroid is going to shift when we remove this corner here. Is it going to move towards that corner where we've lost the material? Hopefully you think no, because if you think about if you move the centroid this direction and you've lost area, the whole shape would tip away from that, right? So really, to balance it, we need to get more material on this side of the balance point than there was before. So it's going to shift in this direction, somewhere down over here we would expect. So our original centroid, if we're looking at X and Y, would have been at 4, 5. Let's find out what it is now. I'm going to use the bottom. This is X and this is Y. So we're going to try to find our new, this would be X bar, and this would be Y bar. So I'm working from basically my origin, if you want to think about that. The bottom and the left are my two axes. So let's start by doing X bar. So centroid of the two shapes. We know the centroid of the big green shape is right there. And we know that the centroid of the red piece that we're removing is going to be right in the middle of it as well. So let's start figuring out what we put in. So for x bar, it's going to be equal to the sum of each individual x times its area over sum of the areas. So x bar is going to be equal to, let's do the big green area first. So in the x direction, the big green area is a distance of 4. So 4 times its area, we've done a lot of times, is 80. And now we're going to be plus the distance to the centroid from this axis here, right? Because we're trying to find x here, so we're balancing everything about a line that's vertical in y. So the distance from the y-axis to the centroid of this one is going to be, let's see, this was, overall we're at 8. So to get up to here is going to be 5. So let me write that out there. This distance right here, that's 5. So distance to the centroid of that is going to be equal to 5 plus then half the width of it. So 5 plus half of 3. So that's 5 plus 1.5, so that's 6.5 times, and now here it's a negative number because we're getting rid of this corner piece. So that's going to be minus, the area of that one is 6 again. So that's our top part of our equation. We've got our distance to the centroid. So here, this is 4 times the area of that chunk that we found the centroid of, plus the distance, 6.5, which is to right here, right, times the area of that chunk, which is a negative 6 area because we're cutting it away. And then on the bottom, we just have sum of the areas. So 80 plus negative 6. So this is going to be equal to 4 times 80 plus 6.5 times negative 6. So that's 281. And as before, we got 74 here. So that's 3.797 inches. So we've moved from 4, we've moved over a little less than a quarter of an inch to where this new x bar, to get to right there, is 3.797 from the left side. So if I come over, .79 is right about in there. So our axis on that direction shifted about that much. And now let's do for the y. So y bar is going to be equal to the sum of the individual y's times individual areas, or the sum of the areas. So y bar is going to be equal to, now we're looking at distance from x. So for the green area, the distance from this bottom x-axis up to the centroid is 5. So area is 5. I'm sorry, individual y is 5 times the area of 80 plus, now it's the distance up to the centroid here, so it's going to be 10 up to here minus 1 to get back down, so it's a distance of 9. From here to here is 9. So plus 9 times, and then the area of that is minus 6, since we're getting rid of it. Okay. And on the bottom, same thing as always. 80 plus negative 6. So 5 times 80 plus 9 times negative 6. On the top we get 346. On the bottom 74. So that's 4.676 basically. Okay, so if I come up 4.676, that would be right about there. And so where those two lines intersect is my new centroid. And you can see it did move in the direction we thought. I had kind of put my mark out there quite a bit too far as far as what it relatively shifted by. But that's where our new centroid would be. So centroid equals, if we're looking at it in terms of x and y, it's going to be at 3.797 and y was 4.676. Okay, let's look at the same one last way now. So we looked at finding this shape that is, let's find another color. We were trying to find the centroid of the composite shape. It's, roughly in this orange shape, right? Kind of a really chunky L, if you want to say. And we did it this first time by looking at the entire rectangle and subtracting the red area. Hopefully it kind of makes sense. There's lots of different ways I could have broken this down, right? Instead of doing it that way, the big blue perimeter minus the red one, I think that's a great way. That's kind of most intuitive maybe. I could have done it several other ways though, right? I could have broken it into two rectangles. I could have looked at, say, this purple shape. That'd be one of my component shapes, and then if I look at this different green shape, I could have looked at it adding these two rectangles together. So let's do that real quickly, and we should come up with the exact same answer relative to this corner down here. So let's do it using these two shapes that I've just added now. This purple one that's a 10 by, let's see, no, so this is 8, so it's an 8 by 8, so that's nice, easy 8 by 8 rectangle plus a 2 by 5 rectangle. So let's do x bar first. So x bar, so we're looking at the distance along the x-axis. So for this first purple area, again that's this square, an 8 by 8 square, the distance to the centroid of that square is just half over, right? So 4 times the area of that square, which we said it's 8 by 8, so that's 64. Okay, that's this first shape, and now we're going to add on to that plus, because in this way of doing it, instead of cutting away this red rectangle, we're adding on this darker green one up here. So now it's going to be plus, and we're looking at x, so it's the distance to the centroid of this rectangle here, which we know that's going to be somewhere right about there, right? So along the x-axis, it's going to be half of 5, so that's plus 2.5 times the area of that rectangle is 5 times 2 is 10. So that's the top half of our equation. And now for the bottom, it's just the sum of the areas. So that's area of the bottom is 8 by 8, so 64, plus area of the top was 10. And you'll see that bottom, we're coming up with the same number as we did before, right? It's 74. Whether we get to it by 80 minus 6 or 64 plus 10, that number should be the same because it's the actual area of the composite shape we're looking at. So this is going to be equal to 4 times 64 plus 2.5 times 10 divided by 74. And so I get an x bar equals 3.797, which, looking up there, you can see those match, right? And then let's do y bar. Okay, y bar, now we're looking at the distance from this axis down here to each centroid. So for the first one, it's going to be the same thing because it was a square, right? We weren't looking at a rectangle. So it's going to be 4, distance from the bottom up to the centroid of our 8 by 8 square, times its area of 64. Now we're looking at the green shape. So distance to the centroid of the green shape is going to be 8 plus half of the 2. So it's going to be plus 9 times its area of 10. And then over 64 plus 10 again. That equal to 4 times 64 plus 9 times 10. divided by 74. We get 4.676 inches. 6. So again, that matches. So it doesn't matter which way we do it as long as you follow the rules. I'm not going to repeat it again, but just to look at it, I could have done it another way too, right? I could have, let me grab a pen that will stand out here. I could have looked at this as one rectangle and then added on this as another rectangle. So lots of different ways to do it, and as long as you follow the rules that if you're looking for the individual centroid of each component piece and you're looking at the area of each component, if you add those together, you'll end up with the same value for the composite centroid. So let's just check and see how we did using our cardboard models again. So for this top one, I have here a piece where I cut out that 1x6 slot. And you can see where our previous centroid was before I cut that out, about our both axes of symmetry. And if I try to balance it on that spot now, you can see that we've lost material up here, right? So now this side that's closer towards me weighs more, is proportionally more than the part away from me. And so it just tips down as soon as I let go of it. But if we move to where our new axis should be, so if it's from the bottom, looks like we were at 4.716. So let's come up 4.7 roughly. It's right about there. Let's try punching through that. Okay, so I just marked it through, and you can see it's balancing again. So it looks like we did a pretty good job finding the composite centroid for this piece with the slot out of the top. Okay, let's come down and look at this bottom one. Again, here's the shape with the chunk cut out, and here's our original centroid. So if we try to balance on our original centroid now, you can see it tipped off in two axes because I've lost material about both x and y. So instead of tipping straight towards me, now it's tipping towards me and to the left. You can see that's kind of the axis it's falling down about was like this. So let's adjust to our new centroid, which doesn't matter which method we did it from. They were both from the bottom left corner. So x bar is over 3.797. So come over basically 3.8. So we know it's going to lie along that axis, and then y bar, so from this bottom left corner up, is going to be 4.676. So I'll set just under 4.7. So that's our new centroid. We think it should be right about there. So push that hole through to the other side. And when I was punching, I didn't do a great job. You can see I'm a little off the line there, but hopefully we're close enough to balance. And yeah, you can see that it's balancing about x and y. So we did a good job calculating that one too. Okay, I think that's enough about centroids. The next kind of related geometric property that we'll look at if we're talking about strength of materials will be the moment of inertia of a shape about an axis, which we denote by I.